Hello, and welcome to this Chemistry World webinar. I'm Mariana Knippers, Chemistry World Science Media Producer. In today's webinar, we will be celebrating a major chemistry milestone. This year marks 200 years since benzene's discovery. Many of you will have some direct link to benzene. It's ubiquitous in modern-day chemistry, from medicine to materials, and even the far reaches of interstellar space. Today, we will be celebrating how far benzene has come over the past 2 centuries and learning more about the historical figures who have made benzene the household name it is today. We are very excited to have 2 guests here to celebrate this special occasion with us. First, we will be hearing from Judy Wu, a computational organic chemist at the University of Houston in Texas. Her work focuses on a wide range of topics, from functional carbon-rich polycyclic anti-aromatic hydrocarbons, photoswitchable molecules, self-assembling organic frameworks, and more. Quite the list. Judy has also currently serves as an associate editor for the Journal of Physical Organic Chemistry. She is highly accomplished in her field, recognized by numerous honors, including the prestigious NSF Career and NIH MIRA awards. After Judy, we will hear from Nazario Martin, a professor of organic chemistry at the Complutense University of Madrid. Martin's research embraces molecular and supramolecular chemistry of carbon nanostructures in the context of chirality, electron transfer, biomedical, and energy applications. He's a fellow of the Royal Society of Chemistry and also held the presidency of the Spanish Royal Society of Chemistry from 2006 to 2012. He is also guest editor of the Royal Society of Chemistry's Special Research Collection, celebrating the 200 years of benzene's since its discovery, focusing on carbon-based systems, aromaticity, and molecular innovation. Oh, it's a lot of big words today. Finally, we will end the webinar with a Q&A session with our speakers, so please be sure to submit your questions. But for now, I'm going to pass things along to Judy for her portion of the presentation. So Judy, if you can go ahead and join us on screen. There we go. We can see your presentation, and now we can see you. Thanks so much, Judy. All right, enjoy, everyone.
Well, good morning and good afternoon, everyone, wherever you are around the world. Thank you, Mariana, for the kind introduction. So today, I would like to start my talk with a question, and that is, what makes benzene so special? Why are we here 2 centuries later celebrating the birthday of a single molecule? Now, if you ask a chemist, they might give you 2 very practical reasons. For one, benzene is moderately reactive, so it's a perfect handlebar that you can just attach different functional groups to make useful compounds. Second of all, benzene is also flat and rigid, and therefore it's a very perfect building block for constructing molecular architectures, sheets, hoops, spheres, tubes, and I think we'll be hearing about a little bit more about it from Nazario later. But there's also a third, and I feel a more romantic reason, and that's the symmetry and the beauty of the molecule. Right here you see, well, humans have been fascinated by hexagons across millennia, and since the Roman times, here you see a Roman mosaic. The floors are tiled entirely in hexagon shapes, and actually the shape is not chosen randomly because hexagon is actually the most efficient way to cover a surface. Therefore, well, you just have to ask a bee to know that that's true. The same hexagon motif also appears across ancient Egyptian, Mesopotamian, Chinese art, and Islamic art. It's really a geometry of order and of harmony. And so you can then imagine how benzene captured the hearts of chemists too, when Kathleen Lonsdale first proved through X-ray diffraction and announced, this was about 100 years after Faraday's discovery, that benzene is in fact a perfect hexagon with equal carbon-carbon bond lengths. Now, this paper reporting the crystal structure of hexamethylbenzene was the first clear proof that benzene is flat and is a hexagon. Here you can also see, this is a work 3 years later, also from Kathleen Lonsdale, her work on hexachlorobenzene. Here you see a projection of an electron density plot, also showing that benzene is highly symmetrical. It's a ring shape. And so I feel that chemists are drawn to benzene, not just because of its reactivity and structure, not just for practical reasons, but also for personal reasons. There's a feeling of familiarity, and there's a connection that comes from its shape. Now, today my talk is not going to be about the science of benzene. It's actually going to be about the people involved in the story of benzene. And with that, let's go back to London in the early 1800s in the era of Michael Faraday. So this is right around the time of the Napoleon Wars. Here. Now, if you walk down Blandford Street to House 48 in London, Marylebone, you'll come across a building with this plaque on the wall, and this documents young Faraday's humble beginning. This building used to be a bookbinding shop. Today, it's a sandwich store, actually. Michael Faraday was the third of 4 children, and he was born to a blacksmith's family in London. And because the family was poor, Faraday only had very basic elementary school education. So he learned to read, and he could write, and he could do some basic math. But by the time he turned 13, he had to start working to help his parents make ends meet. And through his father's connection, Faraday got a job as a newspaper boy and an errand boy for a man named George Ribaut. So George Ribaut also was a bookbinder. And after watching Faraday work for about a year, Ribaut saw how diligent Faraday was, and so he suggested to the boy that perhaps he could come to his shop and work for him as an apprentice, so he could teach him how to do bookbinding. Now, as we often say,
if you could activate I think that's saying this
there is often an unsaturated. In many ways, I feel that George Ribaut was that person for Michael Faraday. All right. Okay, so here you can see a picture of Ribaut's store in the 1800s. Ribaut was a very kind and generous man. He saw how curious and bright young Faraday was, and he really encouraged that. So he let Faraday read all the books in the store, any book that came for binding. He let Faraday attend scientific meetings after hours, which was very rare for apprentices during those days. He also encouraged the boy to try out experiments in the back of the shop. And so you can see that even though Faraday did not have a formal education, during his 7 years at the Ribaut shop, he really gained a lot of the most essential features, characteristics that makes a wonderful scientist. He gained good hands from learning the art of bookbinding. He also read broadly and was in touch with the scientific discussions of the time. And he also actually learned to draw. So there was a portrait artist named John Mascarriere at the time who fled Paris from the Napoleon Wars, and he was sheltering in Ribaut's shop. He taught Faraday how to draw. And so from this experience, he also gained very good observation skills. So you see, he gained good hands, he learned good observation skills, and he read very broadly and was in touch with the current scientific discussions. And so that was a really wonderful education for Michael Faraday, actually. Here you can see a picture of Ribaut showing off Faraday's experiment to one of a customer. Here we go. Faraday also had a very interesting hobby, and his hobby was to take notes. And as a bookbinder, he can bind blank notebooks for himself. And so here you see an example of that. He named this notebook the Philosophical Miscellany. And if you can read the fine prints over here, it says that it's a collection of notices, occurrences, events relating to the arts and sciences. Here you really see a glimpse of Faraday's nature as a very curious an observant person. He would take notes about interesting things that he read about, or he heard about, or he thought about. Here you can actually see an example of a page from the notebook. This is an illustration of the electric fish. It's also called an elephant nose fish. Here you can also see another example page from the notebook. Here he's documenting how to make oxygen gas. Now, during that time, there was also a particular book that influenced Faraday's interest in chemistry, and that was this one that he found in the Ribaut shop called Conversations on Chemistry. It was written by a lady named Jane Marcet. Now, Jane Marcet was the wife of a Swiss exile physician, and so together with her husband, they would attend many scientific lectures. Now, after some time, she realized that while she could replicate a lot of the experiments that she heard about at home, in their home laboratory, many of the ladies that attended the lectures couldn't fully appreciate the chemistry behind it. And so Marcet, being a woman ahead of her time, she thought that women should and could engage with complex scientific ideas. And so she set out to write this book during a time when few women received scientific education. And this book was written in a conversation form, very easy to follow. And so that was perfect for Faraday as a young boy. And for a time, her book was actually very popular and was an introductory book for chemistry in England, and it went through 16 editions. Now, Marcet actually also wrote many other conversations books with the same intention in mind. She wrote conversations on political economy, on natural philosophy, on vegetable physiology, and also conversations on the history of England. Here in this slide, you can see Faraday reflecting on the impact of Marcet's book on his interest in chemistry. He says here, when I came to know Mrs. Marcet personally, how often I cast my thoughts backward, delighting to connect the past and the present. Whenever sending a paper to her as a thank you offering, I thought of my first instructress. Okay, now, near the end of Faraday's apprenticeship, a series of events actually happened, and that led him onto the path of science. At the time, there was a man named Humphrey Davy. Now, he was a professor of chemistry at the Royal Institution at the time, and one of the most prominent scientific figures at the time. And at the time, he married a wealthy widow. Davy is actually known for several things. He's known for discovering several elements by electrolysis. He discovered laughing gas, nitrous oxide, so N2O, and he also invented the Davy lamp. Now, he was thinking that upon getting married, he's going to stop giving public lectures. And so as a final bow out, he decided to give last four lectures. And the tickets to these events were sold everywhere. They were very popular and very expensive. Faraday, as a bookbinder apprentice, of course, could not afford the tickets. But at this time, a frequent customer at the Rebel shop, this man named William Dance, he knew that Faraday would really enjoy attending the lectures, and so he decided to give these tickets to Faraday. He bought the 4 tickets and he gave them to Faraday. And with this opportunity, Faraday bound a blank notebook, again, his hobby, and he filled it with notes and thoughts that he took away from the Davy lectures. And after the lectures, at the encouragement of William Dance, he actually sent the notebook to Humphrey Davy, and that eventually led to a position working for Davy as Davy's assistant at the Royal Institution. This past summer, I actually visited the Royal Institution, and I was very happy to find this plaque at the entrance hall of the Royal Institution documenting this story of William Dance. Now, working for Davy opened a lot of opportunities for Faraday. He got to go on a tour to Europe, and he met many of the most influential scientists of the time, including Ampere and Volta. And upon returning from Europe to England, Faraday actually made all of his most remarkable discoveries in the following 10 years. Now, by 1825, and that's the year that benzene was discovered, by 1825, Faraday had already rose through the ranks. He was not an assistant anymore. He became the director of the laboratory. Now, becoming the director of the laboratories meant he had research freedom. And so he worked on a lot of different public projects. He worked with companies and worked with the government on different projects. During this time, he also became very curious about a procedure of well oil cracking, and that was used at the time for making portable gas for lighting. And here you can see a picture of it. So here you see a picture of a New York home in the early 19th century. By 1825, the streets of London, of Paris, and most of the major cities of Europe were already lined with gas pipes for street lighting. Here you actually see 2 examples of lighting. Here's one attached to the wall, and these little arms go to the back of the wall where the gas pipes run through. You also see here a lamp, which is, of course, not attached to the wall. But at the seat of the lamp, there's actually a little pressurized canister that carries flammable gases that encases flammable gases for lighting. So at the time, portable gas companies like the Portable Gas Company of London would take whale oil and use it to make portable gases to store in these little canisters. So what they would do is they would take the whale oil, drop it in a hot furnace in the absence of oxygen, and that breaks down the components into flammable gases like hydrogen, methane, ethylene, and acetylene, and then you would store it in this little canister. And so during this time, Faraday was very familiar with this process, but he noticed that during this process, an oily byproduct would be produced, and he became very curious about what was in that oily byproduct. And so you can see here, this is actually a quote from the paper that he announces the discovery of benzene. He says here, "My attention was first called to the substances formed in oil at moderate and at high temperatures in the year 1820. Now, eventually he got a hold of meaningful amounts. So he was actually commissioned by the Portable Gas Company of London to do some research and figure out what's in that oily residue. And so he actually proceeded to do fractional distillation. And so that's the easiest way to get different, to isolate liquids out of a mixture. And so he went on to do this fractional distillation, and he found that between 176 to 190 Fahrenheit, large amounts of vapors came out, and he collected these fluids. And here you see in his paper, he announces the discovery of benzene. He says here, "I ultimately succeeded in separating a new compound of carbon and hydrogen, which I may by anticipation distinguish as bicarburet of hydrogen, which is benzene." Now the name benzene didn't come until 10 years later, introduced by Mitscherlich, but this was the first announcement of benzene. And from there, Faraday went on to record the physical properties of benzene and tested the reactivity of benzene. And most importantly, at the end of the paper, which is important for any paper, he makes a projection for what is the impact of this discovery. And so here he says that it is possible that this substance may furnish the fuel for a lamp, it remaining a fluid at the pressure of 2 to 3 atmospheres, but becoming vapor at less pressure, shall possess all the advantages of a gas lamp without involving the necessity of high pressure. And so what Faraday could not have imagined in 1825 was that his discovery, this discovery of benzene, would actually go on to unleash major industrial revolutions in the coming decades. First, the coal tar dye industry and petroleum industry, and then later in the early 20th century, the pharmaceutical industry. Around 20 years after Faraday announced the discovery of benzene, industrial scale productions of benzene from coal tar became very popular. And so many chemists became very interested in doing coal tar research. And what they wanted to do was to see what useful compounds you could synthesize from benzene and benzene-like compounds. Now, a chemist named August Hoffmann at the time, he noticed that benzene and many benzene-like compounds had this sweet odor, and so from there, he coined the term aromatic, and that's where the word aromaticity comes from today. So he used the word aromatic to describe these compounds. During that time, Hoffmann also had a student named William Perkin. Now, Perkin's job, Hoffmann assigned Perkin the job to make quinine. So quinine is a anti-malarial drug. Now today, so remember, this was a time when structural chemistry did not exist. Chemists cared about the chemical compositions of compounds, but they didn't know what structures were. Structural chemistry was still in infancy. Now, if you look at the structure of quinine today, you would realize that actually Perkin would never be able to make it. So now instead of making quinine, he actually made something else. In one of his experiments, Perkin was washing his glassware with ethanol, and then he noticed that a purple solution appeared. And so he was really intrigued by his finding, and so he decided, I'm going to try to dye some cotton with it. And then he tried to dye some silk with it. And then to his surprise, he found that the dye was light fast. And so that means that the color didn't fade when it was exposed to light. So Finally, Perkin never made quinine, but he actually became an incredibly wealthy man and was knighted for his discovery. He quit his academic career and he opened a factory to make synthetic dyes. So Malvine here, this purple color here, and this structure is right next to it. Malvine is actually the first synthetic dye that was ever made. Before this, it was a lot of trial and error. There was no logic behind how do you make a dye. And so by the end of the 19th century, all sorts of coal tar dyes became available. There were blues, reds, greens, pinks, and browns, and the coal tar dye industry basically expanded across Europe. Now, here you can see a very interesting quote. This is actually a quote from the 100th year anniversary of Faraday's discovery of benzene. Now, on the 100th year celebration, Henry Armstrong chaired the organization of this event at the Royal Institution. Now, Armstrong is known for, if you know a little bit about the history of the discovery, the route to proposing the structure of benzene, Armstrong was the person who proposed the centric formula for benzene. And he was also among the first chemists to study how substituents influence the reactivity of aromatic rings. Now, for this occasion, the institution was actually decorated with lots of vibrant fabrics, purples and pinks, and that was to symbolize the very far-reaching impact of benzene from the discovery of Faraday. And so here you can see Armstrong's remark saying that few realize that the foundation stone of the edifice of theoretical chemistry, as well as that of our modern dyestuff and dyeing industries of the wealth of color, was laid there by the act of great Faraday. And so here you can see his remark crediting Faraday's discovery to the foundation of both theoretical chemistry as well as dye industry. Now, as a proponent of fundamental research myself, I really like the story of benzene because I think it is a prime example of how fundamental research can go on to drive industries and applied fields of science. I also like the story of benzene because it reminds me of the very quiet but also underappreciated role that kindness plays in driving scientific discovery. If you think about it, how did Michael Faraday go from the son of a blacksmith to becoming one of the most celebrated scientists in history? So while preparing for this talk, what jumped out at me was just the many forms of kindness that Faraday had experienced throughout his childhood and throughout his path to science. A generous bookbinder who encouraged his curiosity, a woman who believed that science should belong to everyone, and William Dance, who gifted 4 tickets to Faraday, which would go on to change his life. I think that this resonates very, very much with my own journey in science, and it is the kindness and encouragement and opportunities that we receive from people around us that keeps science moving forward. And to me, the story of benzene is really a perfect example of that. And with that, I hope you enjoyed my lecture this morning and afternoon. Thank you, everyone.
Thank you so much for that presentation, Judy. That's a really interesting background on the many characters of benzene. A quick question for you, Judy. Does current science culture still encourage this sort of discovery? The idea that, that discovery can come from these really unique, almost happenstance moments?
I personally feel that the answer is yes, in my experience. I feel that we still do encourage a lot of fundamental research, and my research is fundamental research. So I think yes, yes, I do think we have that atmosphere.
Yeah, it's an interesting thing to discuss, isn't it? We can get more into it in the Q&A session, but thank you so much for that. A really, really fascinating presentation. And you also mentioned Humphrey Davy. Fun fact that this week in chemistry in 1810, Humphrey Davy determined chlorine as an element. Not benzene, obviously, but just you mentioned he kind of was responsible for identifying a few elements there. So just a fun fact.
Chemist and inventor.
Fab. So we are now going to have the presentation from Nazario Martin. Now, let's see, Nazario, can we hear you?
Can you hear me?
Yes, we can. Oh, great to have you, Nazario. Chris is going to go ahead and share the slides for you. So if you just give Chris a heads up when you want to change to the next slide, just let us know and he'll click through those for you.
Okay, that's
Perfect.
very good. Thank you. Okay, so thank you so much, and it's a pleasure to participate in this webinar, and particularly after the wonderful presentation by Judy, who gave us many aspects on the former times of this significant discovery of this molecule. But what I would like to add to this presentation is just to continue to tell you how is the end of the story. So from the very beginning, the discovery of benzene to the current days. So what is going on this time? So today I would like to focus on this kind of birthday, 200th anniversary of the discovery of benzene. That is because the idea is to enjoy with this presentation and without going very much into other aspects, but just enjoying. So the idea is to talk about the time from the chemical structure, from the molecule to the material, which is presented in this slide. You can see, and I would like to tell you about this story that already lasts 200 years. So if we go to the next slide. And this is just summarizing what has been very nicely explained. But this is the first publication of the isolation of benzene, has been already explained with many details. But according to the life of Michael Faraday, you can see that according to this time, he discovered isolated benzene when he was 34 years old. So it is in the next slide, you can see the most typical portrait that is still preserved of Michael Faraday, has been already shown by Judy. And this is, I like to say to students and the people, how in the next slide you see the original sample that has been shown. And this was, I will not go into detail, but it is the first sample that is still preserved at the Royal Institution, London. And I will tell you that this new compound was characterized as something which was a liquid, which was stable and preserved in this state for longer. So, and he was able to report also the boiling point, 80.5 degrees. And if we go, well, it was published by the transaction of the Royal Society of London. And in the next slide, you can see this brief history of benzene from this seminal discovery that Judy explained so nicely. So, but before starting with this very brief history of benzene, let me ask you about the curiosity. I don't know because, well, in the next, please, in the next one, the curiosity is where the name benzene is coming from. Probably just for those people who couldn't hear this origin of this name, is coming from gum benzoin, which was an aromatic resin. From this resin was from in Indochina countries today. It was isolated benzoic acid. It was isolated a substance already known in 16th century. And it was just a few years later, following the discovery by Faraday, L.L. Mitscherlich, just 8 years later, was able to isolate the same hydrocarbon just from benzoic acid, from this substance. just by heating with calcium oxide. And from here, the name benzoic acid was the origin for benzene. So it was in the etymological chain, benzoic acid, benzene. Of course, that could be discussed a little bit more on these aspects, but I think this is very nice to see where the root of this name is coming from. So in the next slide, this is my personal view how the benzene formally, just by putting together many benzene rings, it should be obtained formally graphene. So how was this way from the origin of the molecule to the current day of about graphene? So this started, as has been already mentioned. Please go ahead. With Michael Faraday this year, nothing else to add. In the next one, we can see already mentioned Mitscherlich, okay, and he isolated benzene from benzoic acid. Archibald Scott Cooper, he was related with the carbon tetravalency that was perfect for the next one, which was August Kekulé and the publication of structural theory. And this was practically the starting of aromatic chemistry, but that was mentioned with more detail by Judy. But look at this formula. The formula is by August Kekulé. You can see how it is the double and single alternancy of these carbon-carbon bonds. It is important to mention Kathleen Lonsdale, provided that she was the first person, the first scientist that was able to clarify the aromatic structure by X-ray diffraction. Next one, this was in 1929, and then now we are celebrating the first centennial anniversary of quantum mechanics, and it is necessary to talk about Linus Pauling, who by applying the quantum mechanics to chemical bonding, he was able to tell us about the resonance hybrid that constitute this singular molecule. So these are the famous Kekulé structures and the resonance hybrid that is extensively used in chemistry as well. So necessarily in the next one, we have to see to the famous 4n+2 rule for aromaticity. So Erich Hückel was, with his theory, explained the reason of the stability of benzene. And I would like to continue with a singular person who was living in Spain for a long time as well. At the end of his life, Eric Clark, who firstly synthesized at that time in 1958, although not very nicely characterized, the hexabenzylcoronin, and a few years later, his famous book, Aromatic Sextet. From here on, I would like to mention not the actors, but mostly materials. In 1985, the discovery of fullerenes by Kroto, Smoley, Alcor, and they got the Nobel Prize in Chemistry in 1996. Just a few years later, appeared the other multi-wall carbon nanotubes, in which it was mostly reported by Sumio Ijima in a Nature paper. And just a few years later, in 1993, appeared the single-wall carbon nanotube. And it was, and eventually, just a few later, appeared the famous graphene in 2004. So with this, you can see how the carbon nanostructures, the so-called low-dimensional carbon nanostructure started with the venture of fullerene, zero-dimensional can be considered. The monodimensional carbon nanotubes, either multi-wall or single-wall carbon nanotubes, and eventually the discovery by André Heim and Kostya Novoselov, the discovery of two-dimensional graphene. So of course that there are many other carbon nanostructures, but these are the main ones, and I would like to focus on this journey from the benzene to the graphene. Okay, in the next, it was already shown by Judy, but I like this building and the content of the building because I was visiting, and this is the Royal Institution of Great Britain. It's a quite romantic view in the 19th century, but if we go to the current day, so to the, please, the next one, and you will see here that it is possible to visit the building, probably not with this romantic atmosphere and flavor, but if you go to 21st Albert Mail Street, you can find it. And if you go inside the building, in the next slide, you will see which is the sample which is conserved at the building. And I would like to go back again just to show you that it was probably already known, but the bicarbureted hydrogen. So that means that there are 2 carbon atoms per atom of hydrogen. So the empiric formula should be C2H, which is wrong, but at that time, all of you probably know, the atomic weight and atomic number were not very clear at that year, at that moment. And that is in addition to the inexactitude in some of the analytical measurements could justify this finding. But nevertheless, it was still conserved, these samples at the building. This building, in the next slide, you can see also this apparatus where Kathleen Lonsdale confirmed the structure of the aromatic systems. Actually, it was not with benzene, but hexamethyl benzene, and she was able to determine the aromaticity and the planarity and some of the features of this molecule. So it is also conserved at the same building. And in the next slide, you can see how great countries are able to give the fame to great scientists. This is something which I would like to see also in my own country, but just to put these great scientists in a note is something which indicates how the British people give the credit to the science. Okay, let's go to the next one. And sorry, because it's written here in Spanish, but let me show you some fascinating molecules, like continuing with the benzene containing aromatic rings. And some of them, like you can see here, had been prepared in our own laboratory. So I like to give many examples, but these are beautiful examples where benzene these are what we call molecular nanographenes. And actually, we are playing with two features. One of them is chirality, because you can see in these systems, in the 4 molecules in the up position, all of them are chiral. You can see the helicines in this second molecule, the beauty of the helicine moiety, just connecting to molecular nanographenes. The third one is also another chiral system. These are not cartoon. These are all of them X-ray crystal structures. So in the next slide, you will see that in addition to the chiroptical properties, we are also interested in showing that these materials, which are, I want to remark this aspect, constituted exclusively by carbon materials. So this is pure carbon together with hydrogen, of course, but you can control at will, not only chirality, but also the photophysical properties. What is amazing, what you are seeing here are the fluorescence of these molecules, again, constituted exclusively by carbon, but Also, if you go into detail and decrease temperature, you can find, in addition to fluorescence, phosphorescence, thermally activated delayed fluorescence, aggregation-induced emission, dual emissions, and many, many aspects in photophysics. So this is still something to do in the near future. So let's go to the next slide. And in this slide, I would like to carry out a very short exam for the audience. And here are the questions. Has benzene been detected in nature? So I would like to ask you this question just to clarify the question. I mean free benzene, C6H6. So is detected in nature? And the answer would be, if could be possible to see the many answers, but in principle, yes, because go to the next one, please. And you will see that in nature, benzene is present in many places, in the oil, in volcano emissions, for instance. Of course, when in the fires, particularly big fires like forest fires, we have too much in Spain and Portugal every summer. So I guess that benzene is floating in the air. This, I'm joking, of course, but also in some plants and food, by the way, of course, in very tiny amounts and for specific reasons. So second question, but is free benzene occurring in the human being? Now the question is much more difficult to answer, but here is the solution. Benzene is not naturally produced in the human body because it's teratogenic, and therefore it is not produced in our body. However, if you look at and carried out a very precise analysis, you could, in some cases, detect the presence of free benzene, mostly by inhalation or ingestion. Particularly here, smokers can help you or can help us with by smoking or the polluted air in the cities. And this is the reason, because in probably ppb, tiny amounts could be found, not many. And the last one is, what about the interstellar space? Is benzene over there, is flying, floating on the space or not? And the answer here would be yes, again. So it has been detected benzene, free benzene, although in some places which are not in let's say hot places, like the atmosphere of Titan, which is Saturn's moon, or in the protoplanetary disk, where the temperature is relatively high. There are several reasons for this, because this, for instance, in other cold places like cold interstellar clouds, free benzene has not directly detected, because the radio telescopes are not able to detect this radiation. That is because benzene needs to be in very hot places just to be in the excited state and be detected by infrared receptors. So let's go to the next slide. And let me show you one of the champions in determining organic molecules in the space. There are many around the world, but this is probably the champion one, because today are now over 270 molecules in the outer space, in the interstellar space. Remember that some years ago it was considered to be empty. This is completely wrong. There are many molecules floating over there. And with this equipment, with this radio telescope in Spain, in Guadalajara, in a small village whose name is Jeves, you can see with this beautiful radio telescope with 40 meters diameter. And he has been able to determine around 90 of the molecules existing in the space. So that is because I said the champion. Many of these are aromatic, but be in mind that as it is shown here on the left, this to be detected by this radio telescope, it is necessary that the molecule be polarized. That is because you can see that most of them have mostly a cyano group connected to the skeleton. So this is the astrochemistry is very promising, and is becoming, of course, a reality to understand much better how is the composition. And perhaps in the next slide, we can ask a new question has not been considered till now. If these molecules could have contributed to the emergence of life on Earth. This is a question because the carbon, nitrogen, oxygen, there are a lot of monocarbons, CO molecules in the interstellar space. So that means that perhaps we have to rethinking again about this possibility. Okay, so in the next slide, I would like to show you now which has been the journey from the journey of graphene. Actually, last year it was the 20th celebration of the discovery of graphene. But from our viewpoint, graphene, the story of graphene is not started with the discovery in 2004 of graphene, but actually started just 1 century ago with this paper by Bernal, in which the X-ray structure of graphite was published, and you see that it was identified the graphite structure formed by layers. So from here, the next slide, you can see that well, the first problem came in 1968. Other systems, other papers, at least a couple of papers, previous papers, mention the idea that it was simply impossible, the existence of graphene. It was a mathematical theorem handled by physicists and published in the Physical Reviews journal, which is it's an excellent journal. But can you take in mind that it was considered that according to the mathematical theorem, graphene cannot exist. So now in the next slide, you can see that the ship was moving around, and eventually in 2004, Andrei Heim and Kostya Novoselov, to scientists, they said not only exists, but it is very simple to exist because it can be prepared just by exfoliating in graphite, which makes sense, but nobody did it. So, but I wouldn't like to be the referee of this paper, because if you receive just a paper was published in Science, as you can see here, saying that something which was impossible to exist now exists and has been done just by scotch, by the lamination of the graphite. Okay, Andrei Heim and Kostya Novoselov, the next one, they said just 1 year later that it would be impossible to form materials like microchips, for instance, before 20 years. And in the next slide, you can see that along this time, they were able to get the Nobel Prize in 2010, Physics Nobel Prize, and eventually 20 years later, in 2024, we can say that there are many microprocessors prepared or fabricated from graphene. So this is the journey, like a tale of to go to graphene, to the current graphene, that again, formally, nobody can understand that you can form from benzene, but formally is constituted by benzene ring. So in the next slide, and we are approaching to the end, let me show you the famous paper. This was the paper in 2004. It is something curious. In the title is not written the word graphene. Okay, it was electric field effect in atomically thin carbon films. They never said the graphene, probably because referees could remember this former Physical Review paper and some other previously. So let me show you that in the next slide, you can see what is about this paper. More than 50,000 citations, is certainly one of the most cited physics papers in the history of physics. So it was open, paved the way. Yeah, I'm finishing. Paved the way to the 2D material. So next one.
Nazario, I'm so sorry to interrupt. I just want to make sure that we can get to some audience questions, and we only have 8 minutes left in the webinar. If that's okay. It's been a fascinating presentation, and we are so happy to discuss some more topics now in that Q&A. But for the time being, Judy, if you wouldn't mind joining us on screen, and we'll get to some audience questions. There she is. Hi, Judy. Thank you so much both for really fantastic presentations again. Now, first question that we have from the audience. Idris has asked if the discovery of benzene, could that be considered as the birth of organic chemistry? What do you think? Judy, let's go ahead and start with you on that one.
I would say yes and no. In some sense, it is through the efforts of trying to understand benzene that chemists started to build a system for understanding organic chemistry. And this comes from mainly the works of Archibald Cooper and Auguste Kekulé when they first started to think about self-linking carbons. That was not initially intended to understand benzene, but it led to understanding the structure of benzene and built a way to think about organic molecules systematically. And so it is in parallel to the development of understanding the structure of benzene.
If I am allowed, I would say I would like to add simply that yes, the question was very good. If would say, is the origin not organic chemistry, aromatic organic chemistry? Because previously to this year, the aliphatic organic chemistry already existed. So, and there were many compounds and in a very systematic manner, alcohols, acids, etc. So I would say the question was good if adding the word aromatic organic chemistry. Yeah.
Very fair point. We have, Saddam has asked how the properties, speaking of aromatics, how the properties of aromatic compounds lend themselves to use in new materials. Nazario, would you like to start off this one?
Yeah, sure. Well, that is, we could say that new materials, and particularly 2D materials stemming from graphene, they are formally, again, I want to use the word formally, like the legacy of benzene. Actually, for studying the properties of many, not only graphene and the intermediate materials like nanographenes or even polycyclic aromatic hydrocarbons, can be explained only if you know the aromatic, the chemistry of benzene. So all this benzene is the mother molecule that gave rise to the aromatic chemistry, and therefore, if you want to understand the reactivity of graphene, you must know the reactivity of benzene in many aspects. It's not exactly the same because we are going from the molecule to the material. And understanding the material could be much more complex in some aspects, okay? Because of the limitation of the graphene can be considered infinite in 2 dimensions, but the molecule is the electronic confinement is present in molecules. So it's not exactly the same, but it's necessary to understand it.
Yeah, absolutely. Judy, did you have any thoughts that you wanted to add to that one?
I look at molecules on a screen. Nazario is the expert in the room, so I agree with Nazario's explanation.
That's completely fair. Now, Anita's asking, is there a green chemistry way to produce benzene? Judy, have you kind of worked with any green materials when it comes to benzene?
Again, I think Nazario is the better person to ask.
That's fine.
Well,
Nazario, go ahead.
Okay, thank you, Judy. But I would say that Judy she is also very expert and a wonderful chemistry. So she is producing. So, but let me tell you what I say to my students, they said, okay, so benzene is is producing the cancer, so it's a teratogenic molecule. And therefore, but however, some students tell me, however, we are using toluene as well. Yeah, but the properties of the molecules, if you substitute hydrogen in the benzene molecule by a methyl group, benzene is teratogenic because when in our body is immediately oxidized, not immediately, but it oxidized, and it are produced many derivatives which are able to interact with the DNA. So that is a problem. But when you have the toluene and is oxidized, the first that the students had to know is that the most easy to oxidize is the methyl group. That means that you get the benzoic acid, and the benzoic acid is excreted by the urine. So it is what is in one case as a simple modification like the presence of methyl group makes that the biomedical or biological properties of the molecule can be modified. Actually, just to finish with this, without the benzene molecule is ubiquitous, is ubiquitous. It's I would say in 90% at least in the drugs that people take for illness, you know. So benzene is present because the properties of the compound has been obtained are completely different to pristine benzene.
Interesting. As you were mentioning carcinogens and, you know, cancerous causing things, we've actually had a question. Somebody's asking, how has our perception of benzene changed over the past 2 centuries from a miracle molecule to a known carcinogen? You know, why don't we go ahead?
Yeah, it's connecting and disconnecting.
That's okay. Judy, do you want to have a chance at answering that question?
So I think that it is well known that benzene is a carcinogen, but I think that the main focus now still is what other exciting molecules that we can make out of this framework. And so it is known that benzene is a carcinogen, but I think the more exciting research opportunity are the materials and the useful molecules and the new reactivities that we can harness from this molecule. So I think that is sort of the focus of the field of research.
Yeah, of course. Oh gosh. Well, thank you so much, everyone. I'm so sorry. We have unfortunately reached our time limit, but benzene has been a massively popular subject. So it's really exciting that we had the opportunity to speak with you both. So thank you so much. And thank you everyone for joining us. I'd also like to thank my wonderful Chemistry World digital team as usual. We had Ben Valsler and Chris Pink running things in the background to make sure we all sound and look fantastic. And as I mentioned at the beginning, the Royal Society of Chemistry has announced an open call for a themed collection celebrating 200 years of benzene, which is guest edited by Ben Fringa and our very own Nazario Martin. This collection involves a number of RSC journals and aims to take a broad approach on carbon-based systems for both fundamental and applied research that can be regarded as benzene's direct heirs. You can find out more about the scope of the collection on the webpage that we've just pasted in the chat, and feel free, I think they are still accepting submissions. Thank you all for joining us, and we hope to see you in another Chemistry World webinar soon. I'm Mariana Knepers, Chemistry World Science Media Producer. Goodbye and see you next time.
Bye-bye. Thank you, Mariana. See you soon.
Bye-bye.
Bye-bye.
Bye-bye.